So some remarks. Well, let's finish the proof. So from now, okay, let's take for example the set where the lower derivative is less than alpha. Okay, so we just consider this set here. It is inequality here. So we know that for each x in E, and now you see that there exists, let's say, t, which depend on x, such that, well, t is small. It can be as small as you want, such that f of x plus tx minus f of x divided tx is less than alpha. Is exactly that statement. So the lim converges, so you have something which converges to 0, then I can choose something which is as small as I want because I have a sequence converging to 0 such that is whole. Which means, okay, let's do the drawing here. So this is the point. Now, on which side is defined? So you have this closed interval containing the point. And it is a Vitali covariant. So every point is contained, so this is the definition, from definition. And then you observe that the set, okay, x plus tx, or depending on the sign, x plus tx, x, depending on the sign of tx, is a Vitali covariant. Every point as a neighborhood belongs to one of the family of closed intervals, and these intervals can be taken as small as I want. So I'm very happy now to say, okay, then I can cover my set with cantilever disjoint of these intervals. So we apply, so let's say given an open O containing E alpha beta, open, I can certainly require these intervals to be inside this open set, because we use also in the Vitali when we have to estimate what is left. We remove finitely many closed intervals, and this is an open interval, and we know it's just refine the partition inside the definition. We can take a disjoint family. Let's call these intervals so I. But these are the interval x, xi plus ti. You see why, if you decide on which side you converge, it's easier to write. Otherwise, okay, you have xi plus ti, xi, this depends, and is a family countable among these intervals such that, okay, the first you require that all of them are contained in the interval O. Okay, let's call this interval just for Ix, the one that I choose. Ixi, II. So II is contained in O, and so the measure of E minus their union is 0. This is vitality. I'm pretty fine with the vitality. So what we deduce now? Now we use the condition there. So this condition here means that the sum, so the sum of f Okay. Here I have to write this thing over here. So let's say it's x plus tx minus f of x, the component I, in modulus, which is the length of the interval II, is the measure of the union. Okay, and sorry, this is less than the measure of the union. It's alpha, the sum of the length of II. This is not II, sorry. This is divided by II. And this is the condition where I choose the interval. No? From here, the modulus, well, this depends on the sign of t, but the sign of t is in monotone increasing, so it's the same sign. So I move the modulus here, take the modulus and this guy together. This guy is less than this guy times the modulus of this. But this is the measure of this union, because they are disjoint, and this is contained in O. So it's less than, or less than equal to the measure of O times alpha. So certainly it tells me that whichever open set contains E, its length is larger than this sum. Okay, do you agree? Okay, so this is one part. Now I want to use the other part. The other part is that, okay, we do the same. Take a Vitali coordinate for the second, and here is larger than beta. Take any open set, and then I get that, well, I can require this to be the open set, but this is not important. The important thing is that for every, if they contain an open set, so I get that now I have the sum of f xi plus, let's say, another name, t tilde xi. This is for the f plus thereafter minus f xi is the length of any fat covering of E contained into O using the other relation. So now this guy is greater than beta. So this is less than that. So greater than beta, the sum of the length. Okay, E tilde I. And E tilde I is interval. And now this contains certainly the set E. So it's greater or equal than beta, the measure of E alpha. Okay, now I'm asking you to conclude what we did last time, but it's just from here, so I had the flow. So let's put them together. So the measure of E alpha beta is less than 1 over beta, the sum of this thing. So let's say f plus t tilde. These are other points. These are other points, are not the same. And on the other hand, for any open set contained, which contains the measure of the open set is larger than 1 over beta. And now these are the originals. How to conclude? Yeah, this is alpha over here, of course. And alpha is less than beta. So you see there is almost a contradiction if the two terms on the right are the same. But they are not the same. So you need to require essentially. So I want to say that actually this guy is larger than this guy in some sense. And then it's a contradiction. Because when O is very close to A, these are always the same. And then I have to say that these two are more or less the same. Okay, I'll use that is monotone. Okay, I let this to conclude by because if V contained in O both open and F increasing or monotone, then the sum of F, okay, this is a union of intervals, no? And this is another union of intervals, ij. So let's say ij, and I need to write, okay, ij is x, j, let's say aj, bj, and I call it like ci, di. Okay, so this guy f bj minus f aj is less than the sum f di minus f ci. Well, you just need to, it's almost elementary, no? Because so if you take any partition here inside an interval and the function is monotone, the sum of the increments here is less than the larger interval. Okay, so to conclude the proof is that if I take the second partition to be a subset of the first, which I can do, because in the statement which I can cancel, for any open set you can find a partition which is inside the open set. I can certainly require this thing to be less than this thing. And then I get the contradiction. In fact, the proof is subtle. So let me say the most important fact. So why I need to choose rational?
Maybe
okay, because I want to measure the set E, which is what? The theorem states something about this set, not about this set.
Is the union of this world?
Yeah. Clearly, if they are different, there is some alpha beta such that they are different. But why do I need countable?
Because the measure of interval of rational number is 0.
Yeah, the measure of
An interval with
the measure of the union of countable union
countable union
is
0.
less or equal than the sum of the measures, and each one is 0. So it's okay. And why do I need this guy? See, if they are different, I take, this means that the difference is uniform. It's the set where their difference is uniform. Otherwise, the proof is not working. So if one is lower than the other, I can say, let's take the set where their difference is bounded by a constant, a beta minus alpha. It's for sure controlled by beta squared. It's at least beta minus alpha. Okay, so this is very important, because in measure theory, you know that countable union is fine. And that's why you need countable. And let's see another question. So do I need to localize the stuff in some open set? Okay, so let's do something a little bit more. So assume that f has a derivative which is L1. So what do you think that stuff is going to say about the measure of E? Oh, here I can pass to the limit, no? What is going to converge?
Zero.
It's the integral. This is like, because this is
Like B minus.
it's the integral from one to the other, and then I sum up.
Okay.
So I'm going to let you understand the proof, because the proof is a little work. But if you want to understand why the idea is like so assume that actually f is the derivative, is the integral of a function. So f is the integral from a to x of g. Assume. So this one becomes the measure of E alpha beta is less than 1 over beta, the sum, and then assume that g is greater or equal than 0, so I don't have troubles. Okay, it's the sum, and well, here I have, and assume also that these are just increasing. It's for simplicity. G. But now the integral is countable additive, no? So it's 1 over beta. The integral on my open set O, say, of G. I'm integrating in uncountable many intervals, and they are contained in O. G is positive, so it's bounded by the larger integral, the integral. Okay. Now, take O family which converge to E alpha beta. So, like the measure. So, this converge plus union a set of measures 0. Why we can assume that thing?
Because here f is bounded.
Wait, because it's the very definition. It's the very definition. The measure of E is the is converged. So there is a sequence of open sets which converge, which contains E, and the measure of E is equal to the intersection of these open sets. And then, so I can say a sequence which decreasing of open sets, and their intersection is E, which means exactly that E minus the intersection is measure 0, or the intersection minus E is measure 0, and it's this statement. This is the regularity of the measure from outside, you can approximate from open sets. So now if you pass to the limit, so this becomes On, and that is converged to what? Converges to the integral is continuous. So it converges to the integral over this guy union this guy, but this guy is measure 0, so the integral on that guy is 0 by the very definition of the integral. No? So it's 1 over beta of G. Okay, so and this is equal to the integral of 1. Okay, so what do I discover more or less? Because you see, if there is a set where this is less than beta, I just restrict and I repeat the assumption, so it's a contradiction. I get an integral which is less than 1, and here should be 1. So essentially, this fact over here, if I assume that the derivative exists, means exactly that the derivative is larger than beta, which is trivial if I say like this, no? Because if the derivative exists, this object is larger than beta. But so you understand why the proof works in this way. I have to work around the fact I cannot take the derivative. So the writing like this guy here is the way avoiding writing that the derivative is larger than beta in my setting where I don't have the derivative. And the other I get that is the set where G is less or equal than alpha, less than alpha. Okay, here is larger, I have strict. And then you see it's a contradiction. You can have two sets. A point where a function is larger than beta and lower than alpha. No? Intersection is zero, is empty. Okay, it's a little more clear about this the proof. So it's just a way to avoid computing the derivative, which you don't know yet. But once you know, clearly, it's easy. Okay, so you remember the basic problem we faced was in which sense we can say that the integral of a function is differentiable and is equal to its integral, no? Or vice versa, for which classes you can take the differential, it is an L1 function, and you can integrate. So from this you obtain the following remark. If f is the integral of g, and g is in L1, then f is differentiable almost everywhere, even without using the formula. Why? Because, remember, it is the difference and each one is monotone. So we are very happy, at least I'm very happy, because in some sense, even if I don't know that it is the integral of g, but I know that it's the difference of two monotone functions, is differentiable almost everywhere. So to close the circle is just to say if f prime is equal to g, or f is equal to the integral of f prime. So basically, I have some idea of what I do. No? So I take a function that should be the difference of two monotone functions, and then essentially the problem is with monotone functions. No? So does this hold for monotone functions? This one instead is basically an exercise if you know this formula. And so we have to study that. Okay, before I have to make some exercises for you. So let's take this function. I mean, there is something which is not. I don't know, I usually jump, and that's the problem. I jump too much. See that. Yes, sorry, there was a corollary first. f increasing, then the integral of f prime is equal to f is less or equal f of b minus f of a. You remember that the quantity I want to say if f is equal to the integral of f prime here, no? Okay, proof. Well, now we know that the integral of f prime so f prime exists. And so we can take finite difference. So we know that f prime is the limit of f of x plus h minus f of x divided by h. The previous theorem, for almost every x, this limit converges. And f prime clearly is greater or equal than 0. So no problem in computing the integral. So now the only trouble is, okay, so let's put this guy inside here. When I can do that. So now so let's say, let's compute first integral from a of b f of x plus h minus f of x divided by h. And I have a trouble here because clearly I cannot reach b because h may be, for depending on the sign of h, let's say greater than 0. So here I should put b minus h. Because f is not defined maybe outside the integral. Or you can extend, well, it's not important. But so I want to tell you what is the so I want to use a convergent under the sign of the integral. And essentially it's fine until I can compute the integral for the approximations. So the first step is that if the integral for the approximation is plus infinity, I don't get anything. So let's compute for this approximation and then use a theorem to pass to the limit. Okay, so what is this guy here? Is 1 over h, so this integral is the integral from a b minus h f of x plus h, the integral from a b minus h f of x. Do you see any simplification? Let me say that at the end, when you have to compute something, is like for the Riemann integral. Because Lebesgue, okay, you need to compute, but Lebesgue is just a theory which allows you to define objects. But when you have to compute, it's the same. The derivative is like the classical derivative. At the end, we can only compute derivative of polynomials. And the rest are just formulas. You cannot really say what is the derivative u of x in one point. You can say what is the derivative for any approximation. Okay, so we are here. So this is, I'm integrating from this interval. Okay. Can I change variable?
Yes.
And now it is the integral from Do I need to do a drawing or you see? So this guy is from here with a plus, and then this guy is from to here with a minus. What is left? The two pieces at the end, no? So it's 1 over h. Now, what the plus as b minus h b minus 1 over h. The minus is from a plus h f. And now, so let me add something, for example, and continuous. It's not necessary. Let's say what is really necessary is f of a is equal to the lim of x of f of x. F of b is the lim of f of x. Otherwise, well, these are the values at the end, and you can assume it is the limit values. Otherwise, it's not really. Okay, so what I can say now when h goes to 0? It converges to f of b, because this is f of b plus something which converges to 0, or minus something which converges to 0, times the length of the integral, which is h divided by h. So this is equal to, they converge to f of b. And this guy converges to f of a. For the same reason. So I discover that the lim, so let me cancel. Now these passages are elementary, so let me write this guy together. The lim from h that tends to 0 of this guy is equal to f of b minus f of a. Okay, and now it's just technique. The technique, we know what to use. I want to pass the limit inside the integral.
Yes, fatu.
But we don't know the integrability. What we use. There are, for positive functions, you have two theorems. So the monotone, but it's not the case. I'm not, this one just converges pointwise. I'm not saying it converges point monotonically. And it's false in general, no? And the other is fatu. So fatu. Which in Italian and French is mean really you do everything if you add a T. And indeed, well, you can do everything with fatu.
That's not a. That was not a man. It was not a mathematician.
Yeah. I think it was a calculation. But it's, indeed, we have to add a 2. So here is a 2. Or fatuco. This is Italian. But let me erase it. Yes. They record these French things. Okay, fatu, what it says? The integral of the limit of fn is less or equal to the limit of fn. Okay, very well. The lim is a particular limit. So in this here it means that the integral of the lim of this difference a sequence through a sequence, but we know already that the sequence is converging. Is less or equal than the limit of the sequence, the limit of the integral, which is this guy. But we know that this guy is f prime. And everything is from A to B. if I want to be correct, let me see. Since I fixed h, let's fix h bar. So I have this guy here, then I get h bar and h bar less than this guy. Because, you see, I need to fix this h bar, but there are several ways, so let's do it like that. And then I have that for each h bar, the integral from a b minus h bar of f prime is less or equal than f of b minus f of a. Now I can use whatever you want. Monotone, when h bar converges, the function is converges to the integral. No? This converges if I want to be completely correct. But it's not the only way, no? Because I can say that, okay, is this function times the indicator function, and this converge pointwise again, and then they pass to the limit. You can pass the limit here, or just pass into the limit there. This is, for example, monotone. Okay. So let's rule out immediately something which one may hold. If we have the equality, it's done. The theory closes now. If we have the equality, every monotone function is the integral of its integral, is derivative, vice versa. So it means that the difference of two monotone functions is the integral of their derivatives. Vice versa, if it is an integral of an L1 function, then it's the difference of two monotone functions. So I'm fine. Clearly, this estimate here implies that the derivative is in L1. It's positive and the integral is bounded. So let's see if that's the case. If it is not the case, we have still, unfortunately, another lecture. Here we don't need this, just the proof. Okay, is this function monotone? Yes. Can be the integral of a L1 function without just looking at it. Can it be the integral of an L1 function? Yeah, can a function like this will be the integral of an L1 function? Well, if it is an integral, so remember f of x of g, then I have f of x plus h minus f of x is the integral from x plus h of g. And so when h tends to 0, what I discover?
That's g of x.
The integral of g in a set of measures 0, which is a point, 0. So the integral is continuous. Remember, at the beginning we saw that immediately the integral of a function is continuous, so at least we have to consider continuous classes. So this is monotone, but not continuous. Okay, so we are, this cannot be. And now I'm asking to you, which is the strangest monotone and continuous function you can have it can come to your mind? At the end, the examples are already there.
Monotone, non-continuous?
Monotone, continuous. The strangest.
Monotone and continuous?
Yeah.
The
staircase is the David staircase.
Riemann something. There is a function.
The Vitali function.
Vitali.
the Vitali Cantor, Lebesgue, everybody wants to put his name, this function. So I'm Italian, so it is the Vitali function. In France it will be Lebesgue, and I think in German it is Cantor. So it's the Vitali function, no? So it's something like that. You remember 1/3 here, and then you put 1/2. Then it's 1/9, 1/9, and here is 3/2. Sorry, this is 3/4, and here is 1/4. And then, okay, every time you remove sets, which is 3 to the minus n, and the number of these sets is 2 to the n. To the n minus 1. To the n minus 1. Okay, so the first question. Compute the derivative of f, let's say this function is called phi prime in the open set, which is the union of all the intervals I. So let's say I1, I2, I3, and so on. What is the derivative of f? Of phi? There. Don't get confused. It's zero. It's constant. Is constant in I. What is the measure of O? The computer, no? That's why it's strange. It's 1. So what is the derivative phi prime? Computed like in the Riemann theorem. The Riemann theorem f is differentiable almost everywhere. So what is the derivative? It's 0. Almost everywhere, which is O, a set of which is a full measure. So phi is equal to 0. So this integral is 0. And this guy is 1. Unfortunately for you, we have to continue because now the clock is fine. Okay, so we use in general for f monotone and continuous. The integral of f prime is less than f of b minus f. In general, it means that I have to add some other condition. So let's do another computation. Compute. Well, I think this is stupid, but it's just. Well, I think it's stupid. So yeah. This is more simple. Compute f prime if f is the integral of g, and g is in L1.
G of x?
G of y and dy. This is computed for each point of x.
So, prime is equal to g of x.
Yeah, exactly. But you have to prove it, no? That's the answer. Clearly. That's you have to show that at the end you can assume G positive, so you don't have troubles. And then essentially we can and then we know that the derivative exists. And now there are several ways to prove it. For example, you can just repeat the proof of Lebesgue. When they are different, you get a contradiction. Or when you take the derivative here, okay, because now there are several techniques. I know the exercise is interesting. I don't know. Since there are other techniques you can solve easily with other techniques, but I don't want to use that. So. I would use again. I will repeat the proof of the Lebesgue to obtain the contradiction. Okay, now we introduce then an important class, which is the functional bounded variations. So essentially, this is another class of functions for which describe exactly the case, exactly the region where phi is, or where the family of this function is. So it is monotone, or the difference of two monotones, but the derivative is something more complicated. So the definition is f is bounded variation, which is called BV, and actually sometimes you say NAV, just to specify. If for every partition of AB, let's call it A is equal to 0, less than x, or even less than 1, less or equal than x2, less or equal than xn plus 1, okay, equal to B. The sum of the increments and here the notation is that from I equal to 1 to I equal to 0 to n is less than a constant, less than plus infinity. So no matter how you refine your partition, the sum of the increment is bounded. Okay, let's do some examples. F monotone, F is B. Yeah, it's exactly B minus A. So the sum of this object, no matter what is the partition, is f of B minus f of A. So let's call this the V. But actually, here's some other name. Let's call the infimum. And this is an strange notation because I would call the total variation of f in AB is the supremum among all partitions. Of one of these variations. This is the standard notation, it's not the variation, it is the total variation, we call it the total variation. So from this guy we deduce also if f is the difference of two monotones is, let's say, G minus H, and both are monotone, then f is B, and the total variation of f in the interval definition, well, you have to apply the definition. Here you have G plus A minus H minus G minus H. So now it is less than G minus G plus H minus H. So it's less or equal than the total variation of G, the total variation of F as H. If you have two functions, well, it just is the triangle inequality here. More generally, if it is the sum,
There's plus or minus?
plus, why? Because you don't know, no? Applying f of x, let's say y minus f of x is gy minus hy. And now it is less or equal than this guy minus this guy plus this guy minus this guy. I don't have other inequalities. So for example, then if f and g are dv, so they're bounded variation, then f plus g is dv, af is dv. So it's a linear space. So another exercise is Fn compared to f pointwise. Total variation of Fn of A, or let's say the total variation of f is less or equal than the limit total variation of Fn. Why is that so? Okay, from this definition, there are two cases. Either I can take, let's say this is finite. This plus infinity is the same. So there exists a partition which approximates this guy up to epsilon, the very definition. I take the same partition for a function fn. And now the difference is it is converged pointwise, and this is finite. So when n is sufficiently large, this partition for fn is close to the partition of f, to the value. But for any partition of fn, this is less than the total variation of fn by the definition. So the total variation of f minus epsilon is less or equal than, and when n is sufficiently large, the limit of the total variation of fn. And for any epsilon, so I get the result. If it is plus infinity, there is a sum which is sufficiently large, and it means that this is plus infinity. Okay, so the space is not bad. No? And this lower semi-continuous pointwise convergence, we are fine. Now I want to prove the following. So if f is dv in AB, then f, I write like f minus the total variation of f in AX plus the total variation of f in AX and this is monotone decreasing. Okay, let's add something. Well, okay. Let's put a plus in the minus here, sorry. Monotone increasing. And this is increasing, monotone increasing. It should be increasing. is the difference of two monotone functions. Okay. With this theorem, the BV function is in some sense like the theorem for the theory for monotone functions. Okay. So if you take the space of monotone functions, and you say what is the smallest linear space which contains this set is the BV function, BV space. And let's say these are bounded. For us, monotone is always bounded. So proof. The proof is very easy in some sense. Okay. So let's do like some questions. X maps to TV of f. Now, what varies here is the interval. Is increasing.
It's free. Because it's free.
Yeah, because you add another piece. So if you take the partition for the smaller, you can, and then you just add the partition for the other one, and that's the case. So this is essentially, when you increase x, you can choose the points in a larger set. So you have more freedom, no? It's like the supremum made in a larger set. Is increasing. Okay, so let's prove is enough. F of x minus f of a plus tv f ax. But actually, well, it is enough this guy, but let's see. Here, because you probably have to prove the following. Okay, let's do. I just wanted to jump, but sometimes it's too fast. So I have to prove that. Okay, so the total variation of f in x to y, an interval, because so what I mean is increasing. It means that, let me write it. Because I know the answer, that's the point. For x less or equal than 1. X less than 1. So this reads like okay, now I put this one, so I subtract f of x minus f of y, total variation of f in 0, y, a y minus total variation of f in 0, a x. And then what you can prove is that the total variation of f in a y is equal to the total variation of f in a x plus the total variation of f. Okay, here I have to choose, let's say, the open section. No, it's the same. x, y. Why is that the case?
It's not true. I think is left hand side is big, larger than this one, maybe.
This one?
No, left. This total variation of F on A and Y is bigger than total variation of F, Y, A, X,
Y?
and X.
Just move
No. In example,
this one?
I think it's not equal. It's for example, this left hand side is larger than because any partition of this,
Okay, so this one is larger.
Yes.
So take a partition for this one. So let's say this is x, y, and a. Let's say this is the partition for this guy. Add this point to the partition. If I add a point, it's increasing because I use the triangle inequality. And so it's less or equal than the partition from this interval plus the partition of the interval. So it's less or equal. So at the end they're equal. This is an exercise. It's just a triangle inequality here by adding one point. Okay. So let's do the stuff. So we have to prove this guy, and this guy is equal to this guy. Is that true?
It's 3 or yes?
It's 3 because it's just the case of the C that the most elementary partition you can take, the 2 endpoints. So this is sometimes the fact that it's the difference of two monofunctions is called the Jordan theorem. Just for that. Okay, so the proof is the only non-trivial observation, well, non-trivial, is that if you split the interval, the total variation is the sum of the two total variations. And this is just the definition. So this is the only maybe non-trivial part. So what we deduce? F is dV, then F prime exists almost everywhere, and the integral of F prime is less or equal than plus infinity. So the constant less than plus infinity is bound. Actually, what I have here is the, if you want to try to prove that C is equal to the total variation of F in A, that's a natural choice. Maybe, well, we know that is the difference of two monotone functions, bounded monotone functions, so certainly we know is the difference of the two objects. Okay? Okay, so we discover another important class. This is more important. It's a very important class. So let's say the classes of functions. Okay, so let's start with the easiest. The easiest are the Lipschitz function. The function such that, well, there exists L, and f of x minus f of y less or equal than L x minus y. Then this is what we use earlier. Then we have, well, the function which are,
Bonded to origin.
put it here. Now we have the continuous in some cases. Then we have the monotone. And still there is a class which is missing, that f is the integral of g in L1. Okay, this class is called the absolutely continuous function. So far, which inclusion we have discovered? The monotone is contained in BV, but is not contained here. If it is the integral, is the difference of two monotones, so certainly this holds. This holds, but they do not need to, this guy, they have an intersection, but they don't need any inclusion. So now we have to finish by defining what is this class. And then show that Lipschitz is okay. And okay, and the rest is the only inclusion that lacks. So that the Lipschitz function, the Lipschitz function is contained in BV.
Yes.
So we know that. So if I can prove this is the future, this inclusion, then I'm fine. Okay, so just one simple exercise. F is x squared cosine of 1 over x minus 1, 1, and g is x cosine 1 over x, let's say sine, in minus 1, 1. Which is BV, or are them both BV? Just none. You don't get confused, because at the end I told you, when you have to compute something, it's like you have just to do the classical analysis. Classical analysis for computation. Then you have this analysis which is just to prove statement. You take the derivative.
Doesn't belong to B.
So I'm using the following exercise. If f is C1, then total variation of f in A, B is equal to the integral of modulus of f. You use the definition. For any part, it's really the definition of the Riemann integral here. For any partition, this is the sum of the integral of the absolute values. And essentially, when you squeeze it, it converges to, well, when it's positive, when it's positive, when it's negative, it's negative. So the end is this guy. Okay, so we need to compute if the derivative is L1. No, so it means that the derivative should be L1. Okay. So let's compute. This is f prime. Okay, you can do that. One is yes, one is no. The other is no. Okay, so let's see. By Friday we have to finish this. Absolutely continuous function. And this is the last class. Say that I don't understand that the part absolutely continuous, but just to say that it's stronger than continuity. Oh, how to reach then this thing? So this I open a parenthesis because it's better to understand why the object arises. The object arises, not at the end what is the definition. So why the object arises. So we saw already something like, let's say, when you have a family of functions and then you want to have this family of functions to have uniform integrability. You remember, no? Essentially, if I take, give me epsilon, then I take a delta. For any set less than delta, for any f, the integral in that set is smaller than epsilon. For one f is trivial. So assume f is the integral of g and g in L1. So it's an integral of function. Then g is, so the following condition holds, no? So for all epsilon, there exists delta, the integral over, if the measure of a set E is less than delta, then the integral over E of G is less than epsilon. Simply because you cut the parts where it's large, the rest is finite, and then you're fine. So how to restate the object here? Well, I have a trouble because the integral of the modulus is not f, but clearly I can reduce. In particular, if E is less than delta, is like you say open set. So is the union of counter remaining disjoint intervals. Let's say AI, BI. So the integral over E is the integral over the sum of each interval, no? Okay, still is not f, but clearly this guy is larger than the sum of the modulus. This is the monotonicity of the integral, no? G is less or equal than its modulus. And now this is f. So we discover what is the definition of absolutely continuous function. This is a condition that you need to have, and it has not been written earlier. It's not the continuity, no? So now we take it as a definition. F is absolutely continuous. So it's in AB. If for all family of disjoint intervals, well, let's say like this, is for all epsilon, there exists delta such that if the family of disjoint intervals satisfies the sum of the length of the intervals is less than delta, then the sum of the jump of the variation is less than epsilon, and okay, I mean that AI is AI. Okay. So you see the definition is quite natural. It's actually natural. If you require something, you use that thing is uniformly integrable, and then you obtain a condition which is called absolute continuity. So the absolute continuity recalls the fact that the sum is taken in modulus. It is not taken as the modulus is outside. 5, Vitali function. We question whether this function is absolutely continuous. Is it function absolutely continuous? Then this condition is nice, but doesn't say it's not the correct one. It's not just that. Okay. Here. Okay, can you see which will be, okay, of course this will not be absolutely continuous, otherwise we need 30 lectures. So, which will be the bad set? I have to prove this is not absolutely continuous. So I have to prove that there exists a bad set that whatever is small,
Counter set in this case.
the counter set, yes, is not an open, so what you take? An open set containing the counter set. Let's say the counter set is the 1/3 counter set. And the measure of O can be taken less than delta for any delta. Because the counter set is measure 0. No? What is now the variation there? I state that the variation is 1.
Every this interval contains at least one counter point or no?
It's the difference, plus another difference, plus another difference, plus another difference. The sum of this variation is 1.
Monotone.
It's because it's monotone, yes, otherwise it can be larger, but it's a 1 in this case.
Yes, it is.
Okay, it's not absolutely continuous. And something easy. F Lipschitz is it absolutely continuous? Yes. Can I estimate epsilon?
Yes, L.
Is L times delta. This is less than L, the length. Oh, so the inclusion is fine. You remember the picture. When the Lipschitz enters into this absolutely continuous function. And, well, now we have to prove that it's BD. And then we have the picture of inclusion of spaces. We have seen already the idea to do that estimate.
So,
For the uniform integrability. If you remember the uniform integrability, we say, well, at the end, if a family is, well, I think use uniformly integrable, then what it uses that, well, at the end, if you take any partition, you just take partition of size delta, so size delta, and then the variation tells you that inside that partition is less than epsilon. So at the end, how much can be the total variation? So let me, I make the picture, and then I hope you understand. This is A, this is B, and then I essentially take a partition. Now I add points in order to make exactly the partition at size delta. So let's say this is A plus delta, A plus 2 delta, and I go on. So I add these points. So if I add points, the partition, essentially the variation increases because I'm adding by triangular inequality. It was our observation. No? So it's the sum for the first partition plus the sum, the variation for the second plus the variation for the third. How much is the variation inside here? It's written. So the variation inside here is at most epsilon. Here is epsilon, epsilon. So how much is the total variation at the end? Is epsilon. Or I can write it. This is the sum of the total variation of f in A plus, let's say, n delta, A plus n delta plus 1.
Delta plus n plus 1 delta. N plus 1 delta.
Yes.
So it's epsilon inside.
Vediamo. So the picture is complete now. The functional spaces are, well, at least from the point of view of the functional spaces, we know where to put each of the functional spaces.
Absolutely continuous function is continuous, or absolutely continuous function is continuous.
Just take one interval. When epsilon, delta goes to 0 means that the difference of the point goes to 0 and then goes to 0, yes. Okay, I don't have time to go on, so let me see, maybe some exercise. Because the last part is to prove that, so the aim of Friday is to prove that the derivative of absolutely continuous function exists, but now we know that actually not only it exists, but the integral of the derivative is the function. So this is the end of the story, no? So the end of the story f is absolutely continuous, then f is BD, and then f prime exists almost everywhere. So end of the story. F is equal to the integral of f prime. Actually, f prime is 1. We know also that part. And so we have answered the question we had Friday, which is the class where you can, well, the fundamental theorem of calculus hold. Is the class of absolutely continuous functions. Actually, this is the theorem, but we need some tool. So let's do some exercise. Oh, well, at the end is finished the lecture. Okay, so Friday we do the theorem, we do some exercise, and we do something like for convex functions. And that is the end of this chapter. And then what is left, and usually is not, also last year, is impossible to do, is to prove some theorem for general measure theorem. We have to compress it in 2 hours because that theorem is fast. And so we have to prove, to show that all the theory we did, if we replace the Lebesgue with and the R and the measurable set and the Lebesgue measure with another measure space, everything is fine. But still there are some theorems we can improve. So for example, we have to write what is the Lebesgue measure in RD and prove the Fubini theorem, which is the iterated integral. And then we have to prove also that the decomposition of measure with sign and the derivative of measure with respect to the other. So you can do a little bit more analysis. And with that I will finish. So Friday and Wednesday I will finish. Next Friday, which is the last, I think I prepare, the time is running, of course, some exam like form. So you just can try to do the exercise. I give to you, there should be 4 or 5, and they have 10 exercises each, something like that. You can try, and then essentially the exams is much easier than what I give for the for exercises.
When will be
Is it January? January, because I'm leaving.
Do you know the
For
date?
work. 8, it seems to me. They told me 8. I can check.